All right, so now we are going to start tinkering with exponential functions, okay? Now, just to kind of give you an idea of what an exponential function is, let's compare it to linear. Linear functions are of the form y equals mx plus b, where that's the slope and that's the y-intercept. The y-intercept, that gives us the starting point, and the slope tells us how fast things are growing. Now, exponential functions are similar. They're often written in this format, a times b to the x, where a is the y-intercept, the starting point, just like this guy. So they're the same. Actually, they are the same thing. They tell the same thing. And this guy, similar to m, the b tells us how fast things are growing. However, instead of x being multiplied by that number, x is using that number as the base of its exponent. So the relationship is a little different, but fundamentally it's still kind of the same idea. So with linear functions, you get straight lines, as in, because that's the root of the word linear. Okay. And if m is positive, it's an increasing function from left to right. And if m is negative, it's a decreasing function from left to right. And with linear, you always add on the same amount. So for example, if let's say that you are selling basketballs at the store, and you say, all right, this month we ordered 5. Next month we ordered 8. The month after that, 11. The month after that, 14. You're always adding on the same amount. You're always adding on 3. That is an example of linear. Now, exponential would be more like this. Hey, we start off with 5 basketballs, and the next month we order 15. And the next month, 45, and the next month, 135. And so this time, yeah, we're starting off with 5 again, but instead of adding 3 every time, we are multiplying by 3 to get the next number each time. Okay, that's the difference. And so with exponential, it grows much more quickly. Now, the graph of an exponential function, if it's increasing, it looks like that. And if it's decreasing, it looks like that usually. I mean, you can do things to them, flip them around and stuff, but that's pretty much it. All right. So those are sort of the basics, some of the basics of exponential functions that you'll definitely want to review. So graph the exponential function. Well, like we said a moment ago, that's like our a, our y-intercept. Okay. And let me so we'll make a coordinate plane here. And let's go back to this guy. Okay, so this guy right here tells us the y-intercept. So we got a y-intercept of 4/3. That's 1 1/3. So a little over 1. And it says that we're going to be multiplying by 3 every time. Okay. Which means it's going to be increasing. It turns out that if this number, the base of the exponent, is bigger than 1, then it's going up. And if it's less than 1, so it's a fraction, like a half or an eighth or something, then it's going to be decreasing. So, so yeah, so it's going to be looking about like that. Now, they say plot 5 points to make this happen. Well, this is what it's going to look like, and you can confirm that on your calculator. But you know, let's go ahead and plot 5 points. I mean, what more could a guy ask for? So let's go like this. So we'll say, all right, we're going to have some x's and y's. And well, we already know that when x is 0, y is 4/3. So maybe, I don't know, we'll plug in a couple of x's over here, a couple of x's over here, and just sort of see what happens. Okay. So when x is -2, we get 4/3 times 3 to the, you know what, I'm just going to do this on the calculator because this is going to be really tiresome. Hang on a second. All right, so I've got my function in the calculator, and I'm going to go to the table, and hopefully I've got what I want. All right, so the top 5 lines. So we've got 0.1481. We could do it by hand to find out exactly what that is as a fraction, but whatever. So, oh, I don't need to go back, do I? Anyway, so these guys right here are those 5 points I want to graph. And if I graph them, you know, like when x is -2, for example, that's, I need a different color so you guys can see this better. Let's go that color. So when x is -2, we're only at height 0.148. Okay, so that's going to be down here. It's actually a little lower, but you get the idea. And then when x is -1, the height y is 4/9, just under a half. Okay, so that's actually, yeah, so my line's a little higher than it should be. And then when x is 1, the height is 4. Okay, and actually it looks on mine like it's about height 2. So we probably should probably should just make our own graph starting from scratch. Okay, and let's see, that's 12 because I need to go up to height 12. So that's 6, 3, 9. On the x-axis, it's just 1, 2, -1, -2. All right, so all right, so when x is -2, y is 0.14. Just so it's pretty close to 0. So I'm going to go right there. And then when x is -1, we're just below a half on the height. So it looks a little higher, not much. And then when x is 0, y is 1 1/3. So a little higher there, not much. When x is 1, y is height 4. So now we're there. And when x is 2, y is 12. And you can see that, yeah, that traces out an exponential looking function. And that's all you do. Okay, so here we go. Got the graph of an exponential function, and we are supposed to find the domain and the range. Okay. Now, there's this dotted line thing here. That's an asymptote, in this case, a horizontal one. And that just tells you or governs the end behavior of the function. You'll notice as the function heads off toward the right, it gets closer and closer to that dotted line. And in fact, in the picture, it looks like it's actually hitting the dotted line. In reality, it probably is not. Most likely is not. But it just gets really, really close. Okay, so just looking at this, what might the domain be? Well, the domain is all the x's that are being used. Clearly, we're going out this way forever. But what about that way? Are we going to go on forever that way? It looks like it, yeah. I mean, yeah, it's going down forever, but it just keeps getting, as you go to the left, it just gets further and further and further and further to the left. So looks like it's going to go infinitely far to the left. So we're going to go -infinity to infinity for our domain. And then for the range, let's see, the range is all the y values being used. Well, we're certainly not using any of these y values. In fact, we're only using y values from -1 on down. Those are the heights that we're using. So it looks like all y values that are less than -1 or -infinity to -1. And that's kind of it. It's just like domain and range for any problem from the graph. All right, so graph the function. It doesn't ask for 5 points, but it asks for 2 points. Okay, well, that's cool. Well, let's see what we can do here. Oh, I like using x equals 0 because that tends to be easier. So when x is 0, y is -2. Wonderful. How about when x is 1? When x is 1, y is 1. Neato. Neato burrito. Okay, so we know that 0, -2 is a point on the line. And we know that 1, 1 is also a point on the line. Okay. So that's cool. And it says, all right. So now it says use the graphing function on Alex to graph this, because if you're gonna just kind of wing it like we did on that other problem, yeah, 5 points is going to work better. But when you graph it with the Alex function, it can handle this. Anyway, it looks about like this as an exponential function, roughly. It says, oh, we also want you to draw the asymptote. Well, one way to do that is to say, all right, if it was just 4 to the x and there was no -3, the asymptote would be, the horizontal asymptote would be the x-axis, because that's just sort of the default asymptote, horizontal asymptote for exponential functions. But there is the -3. What does that -3 do? Well, it just moves the whole graph of the function down 3. So without the -3, it looks like this. Okay, and the whole thing got shifted down 3. So the asymptote got moved down 3. So the asymptote, which was y = 0, the x-axis, that got moved down to, went down to y = -3. Now, if you don't believe me, and well, knowing me, I suppose that makes sense, you could check it on your calculator. Let's take a look at that. All right, so I got the function in there. I hit the graph. It looks like what I drew, except it looks better, smoother. Okay, what about the asymptote? That horizontal asymptote, what height is the function settling down to? Well, if we go to the table and we look at x values that are further and further to the left, okay, does it look like the y values are getting closer and closer to something? Why, yes, -3, as a matter of fact. So yeah, so they are getting to a height of -3. Therefore, the horizontal asymptote must be y = -3. That settled down to it fast. Wow. All right, then it says find the domain and range. All right, let's go back to the good picture. So the domain, once again, is going to be all real numbers, because it goes infinitely far to the left and it just keeps getting wider and wider to the right as it goes up. So the domain is going to be all real numbers, or -infinity to infinity. All right, the range is going to be everything bigger than 3. Okay, we got that horizontal asymptote there. It doesn't go below that, so it's going to be all y values above 3, or in other words, 3 to infinity. I'm not putting a bracket on the 3 to include the 3, because I know that the graph of the function actually doesn't hit 3. It looked like it on the table, but that's because it couldn't show enough decimal places. It's going to be like, or I'm sorry, -3. But on the table, the y values corresponding to those x values that we saw on the table are actually things like -2.99, -2.9999, but it never does get to -3. Okay. All right, so on this one, the dollar value v of t of a certain car model that is t years old is given by the following exponential function. All right, so let's see what we notice here. What's the starting amount? Well, that's the number out front that is not raised to the t or x power. Okay, so the starting amount, starting value of the car is 27,500. Does that seem reasonable? Yeah, it seems reasonable. Some cars are cost that much when they're brand new, at least when I made this video, although they're definitely going up these days. So 27,500 would be the beginning value of the car. Now notice the base of the exponent. It is between 0 and 1, okay? Which means that the function is not increasing, the function is decreasing. Well, that makes sense because the function measures the value of the car, and the value always goes down, okay, unless you got some fancy classic or something, but even then, not at first. So yeah, the value goes down. That makes sense that we would have a decreasing function instead of an increasing function. If it was increasing, it'd be like, oh yeah, the value just keeps going up and up as soon as I buy it. It's like, well, that's not, I bought it for 27,000. Next year I'll sell it for 40,000. That doesn't make any sense. Okay. All righty. What else we got here? So we know that, yeah, so the function is going to do that. What was that? Oh, yeah, right. Okay, and we know just from the basic function notation that value of this function calculates value, but it's based on how much time has passed. There are other factors like how well have you taken care of the car and all that, but the value is a function of how much time has gone by, or the value is dependent on how much time has gone by. All right, so we got this. Find the value of the car after 7 years and after 13 years. So all we're doing is V of 7 and V of 13. Okay, and give me a second. Okay, so upon evaluating that, after 7 years, the car is down to only $4,831 approximately in value. Wow. Wow, wow, wow. That's a lot of value that went out the window. Okay, well, what about 13 years? Okay, well, now we're down to $1,080, about 88 bucks. I'm rounding this stuff up, but that's okay. So, this is an exponential function. I know that because the independent variable is in the exponent. It's not linear. So notice, in 7 years, the value of the car goes from 27,500 to 4,800. So you lose around $23,000 in 7 years. In 6 years, from here to here, you only lose like about $3,800. But up here in 7 years, in about the same amount of time, you lose way more. That's the nature of exponential functions. Okay, at first, when it's decreasing, it just drops like a rock. But then after a while, it flattens out, and you're not losing much each year. With an exponential increasing function, it starts off real slow, things aren't growing very fast, and then it really starts picking up speed and things are really growing. Okay, kind of like, when you invest money or something for a long time. Anyway, so that is kind of the idea there. Now, another important feature about all this is the fact that what does this 0.78 mean exactly? We said because it's between 0 and 1, that means that it's an exponentially decreasing function. But that number tells you what percent of the original amount you're going to end up with each year or each hour or month, or whatever the time unit is. And so it says, hey, you're going to end up with 78% of what you started with. So after 1 year, you end up with 78% of that. After another year, 78% of that. So if you end up with 78%, you are losing 22% every year of whatever the current value is. Let's see how that works. Just real quick on the calculator, where life is wonderful. So the value of the car is 27,500. And let's multiply that by 0.78. So we're just going to keep 78% of it. All right, so 1 year came and 1 year went. We're down to 21,400. So another year comes and goes, year number 2, and we keep 78% of it. We lose 22%. And we keep doing that for 7 years. Okay. Times 0.78. Okay, so there's 3 years. 4 years. 5 years. Only 2 to go. 6 years. Times 0.78. Yeah, whoa, look at that. There's our 4,831, just like we had over here. That's all that's happening. An exponent, that's all the exponential function did. All it did, but instead it said, hey, you know, this isn't time for amateur hour. Let's just take the 27,500 and let's multiply it by 0.78. But let's do it 7 times. And we get that. But isn't that what we did to find v of 7? We plugged 7 in for t. And we did exactly this thing right here on the calculator, which is the fast version of all this up above. So that's kind of what's going on there to help you understand exponential.